A normal distribution is the essence of random chance fluctuation. Suppose I've been practicing for weeks to estimate in my mind a 10-second interval.
I use my smartphone pressing start on the stopwatch app. Then, without looking, I attempt to estimate when 10 seconds has elapsed, and I hit the stop button when I think it's been exactly 10 seconds.
When I first began practicing 2 weeks ago, I wasn't very accurate. You can see that I had a lot of variance, but there was a bell shape to my distribution. Here are my results over the past week. There is much less spread in my results, indicating more accuracy on my part, and my results tend to follow a normal distribution. This is because a normal distribution tends to be the results we get due to random chance fluctuation. At this point in my practicing, the results tend to follow a normal distribution with a mean of 10 seconds and a standard deviation of 0.2 seconds. In a normal distribution, we should find approximately 68% of scores, times in this case, within 1 standard deviation of the mean, 95% within 2 standard deviations of the mean, and about 99.7% of the scores within 3 standard deviations left or right of the mean. This is known as the empirical rule, or the rule of 68, 95, 99.7%. Again, this tends to be how random behavior fluctuates in such a setting. My estimates on the stopwatch will tend to be close to 10 seconds with a little deviation above and below. 68% of my results would be from 0.2 seconds below to 0.2 seconds above the mean of 10 seconds. 95% of my times within 0.4 seconds of the mean. Only 5% of the time, due to chance fluctuation, will I be off by more than 0.4 seconds. Heights of women are normally distributed with a mean of about 65 inches and standard deviation of 2.5 inches. Use the empirical rule to determine the interval containing the middle 68% of heights. Knowing the distribution is normal allows us to place the mean in the middle and add 1 standard deviation above and below it. The middle 68% of heights, therefore, are between 62.5 inches and 67.5 inches. Middle 95% of heights are from 60 to 70 inches. If a car was produced that was too big for a person less than 60 inches tall, what percent of the population would be too small for the car? Well, since the middle 95% is between 60 and 70 inches, and since the normal distribution is symmetric, it must be that about 2.5% of women are below 60 inches and 2.5% are above 70 inches to account for all 100% of the heights. Thus, 2.5% of women would be too small for this car. What percent of women are taller than 65 inches? Well, this is the mean. It's also the median, so the answer is 50%. Use this understanding to estimate the percentage of women who are taller than 67.5 inches. Well, 68% is in the middle, and the distribution is symmetric. Thus, 34% are between the mean and 1 standard deviation above the mean. Altogether, there's 50% above the mean, so this leaves 16% above 1 standard deviation, and this is our answer. One last important thought for now. The variable that has a normal distribution must be continuous. Heights of women are continuous. If a woman claims to be 5 feet 8 inches tall, and we could measure her height to 10 places past the decimal, her height may actually be this. So there's pretty much no chance of her height being exactly 5 feet 8 inches. For this reason, if we ask to estimate the percentage of women who are at least 67.5 inches tall versus how many are taller than 67.5 inches, there is relatively no difference because they only differ by including or excluding one height, the height of 67.5 inches. A bell-shaped distribution for which a variable is discrete can never be normal due to lack of a continuous number of values. However, we're going to see later in the course that we can approximate discrete variables that would otherwise be normal.